quite a few people here. So first, thank you very much to come to the recitation. It's totally voluntary, and you don't really have to come if you don't want to, especially today is a holiday, I just realized. And I'm grateful that you all presented here. So today we're going to talk about a deep learning package. It becomes increasingly popular called PyTorch. So how many of you have heard PyTorch? Okay, most of you. Now I'm thinking why I'm covering this. But anyways, so the reason I'm giving this recitation is not saying I'm going to cover every single detail of the PyTorch or make all of you become a middle-level PyTorch coder. It's just to make you guys comfortable enough to start the final project. I think the final project is posted. Is it posted? No? Well, anyways, so it should be something about the deep learning. And so from this, I would like to give some basic concept operation that is defined in PyTorch. And so that you guys, when you guys do the homework or the final project, you guys are comfortable enough to start searching, hacking around, and so that it's not too difficult to get the project down, all right? So first thing is, so let me do another question. So how many of you use any deep learning package before? So what package did you use? Cafe, nice. Did you use that like kind of years ago or like quite recently?
Last year.
Oh, last year. Because Cafe is kind of is not maintained anymore.
Oh, is it not?
No, it's.
Oh wait.
Or Cafe 2.
Now?
Yeah,
Oh,
Cafe
I was
2.
using Cafe.
Ah, right. Cafe is a very classic. It's a first deep learning platform, which is the developed in UC Berkeley, but now it's more integrated into PyTorch.
Oh, okay.
So I see several other people raise a hand. So what did you use? So you said you used TensorFlow. Very nice. All right. So I think instead of I put this PyTorch installation here, but since some of you already have some experience, so let me just first talk about why I'm going to cover PyTorch. And you might find out not very convincing because, so here is a package comparison. You have Theano, TensorFlow, Keras, which is basically a more high-level package with the backend of TensorFlow and Theano. And Cafe, of course, the first one, Torch, PyTorch, MXNet, or the other one, CNTK, which is a Microsoft one. The chainer, I don't really know what it is. But from years to 2014, where the deep learning method and packages really take off, and you can see this trend where, of course, Google's TensorFlow is dominant, but Facebook's PyTorch is here, and it has increased. The speed of its increase is really fast. And if you look at the publication in arXiv this year, and PyTorch now is ranked number 2 for the research purpose. But why I don't cover TensorFlow? I will talk about that a little bit later. So second thing is about the speed. So the performance of the package, if you're working on a specific like just CNN, VGG network, or RNN or ResNet, so you can see the basic performance of each of them are kind of quite different, especially for RNN. The PyTorch has a very good performance on RNN. The TensorFlow, not so much. So let's go to a little bit more detail. So I will just cover basic difference. I think Keras and PyTorch probably more beginner friendly. TensorFlow is a little bit more, you need a little bit more understanding and need a little bit more coding skills. But Keras basically is you can use as a wrapper of TensorFlow. So Keras has a very simple syntax, and all the model units, like the convolutional layer or the max pooling layer, they're just like a Lego like a model. It just say add this, add that, add this, add that. And it's very readable because it's just one line of adding a specific layer. But this kind of encapsulation make it very easy to read in a high level. But if you want to do any low-level manipulation, it becomes very hard. PyTorch, on the other hand, is very flexible. It basically shows you most of the details of the deep learning package. It's also dynamic. Dynamic is one of the main features of PyTorch over TensorFlow. So TensorFlow is, we'll talk about that a little bit later when we talk about building a computational kind of like a graph thing of calculating especially for calculating the gradient for backpropagation. But dynamic means that you can run just like MATLAB. You can run and see the results every single line. So for TensorFlow, you have to define it, you have to start a session, and it's very difficult to debug. And trust me, you really want a language that's very easy to debug. And because PyTorch is also show you a lot of details, it also encourages you to understand a little bit more of the basic concept of the deep learning, so that you can be aware of many of the details that many of the other package hiding from you. But PyTorch is just for Python, as named. TensorFlow, Keras, they are more versatile. They are more. They might focus. If you are working in R, C++, you might just want to just directly go to Keras, TensorFlow. PyTorch might not be a very good idea in that sense. So I think that's, yeah, so this is just one remark from one guy. So Mr. Karpathy, if any of you know this guy, he is the head of the Tesla's AI department. So he says, been using PyTorch for a few months now, and I've never feel better, because he was using TensorFlow. And I have more energy, my skin is clear, and my eyesight has improved, because debug in TensorFlow is very difficult, but PyTorch debug is very simple. And so with that, let's go back to installation. So PyTorch installation, it's similar to many of the Python packages. How many of you already have experience in Python or Anaconda, let's say? Okay, so I think half of them. Good. And so Anaconda is a basic compilation of Python packages that basically contains most of the packages you want to use. So you just go to Anaconda's website and download Anaconda, and it provides 99% package you want to use. So PyTorch is also in. You can also install the PyTorch using Anaconda. So, well, all the basic package is provided. It's a nice environment management by Conda. So when you do Python coding, you might have different version of Python. You might have different version of NumPy, SciPy, all of those packages. So you may want to create an independent managing environment for PyTorch. And all of those are nice features. So those are more detailed, like you guys can, I'll post it online and you guys can just refer to it when you want to install the PyTorch. It's just there. And those PyTorch packages should already installed in our EC computing lab. So you guys don't really have to install it, but if you want to, just for practice, you can. I'll just post it online. So now let's go into give some examples. of the PyTorch. So here I'm starting is a Jupyter notebook, which is an interactive coding environment. I can type the code in Python and it will run and it will show up the results just in this website. A very nice interactive environment. So if you might want to use it as part of your report, that you just show this line and show the result. It's totally acceptable and it's encouraged. So if you want to, any of you have the computer, you can also access to this. This is basically, the following tutorial is mainly based on a 6-minute tutorial provided by PyTorch. So if you just search for, let's say, I think it's this. So if you search deep learning with PyTorch, a 60-minute blitz, you will find out most of the materials I'm going to cover. And I will also post the Jupyter notebook in the Carmen so that you guys can refer to that. All right. Okay, so let's get started. So after the PyTorch installed, the first thing is you want to add the PyTorch into the path that Python is searching for. So import this module, import torch, not PyTorch. Import torch will have you, let me see this. Oops. Is this. Right, so now the first thing is what we can do, the basic structure in the PyTorch, like the vectors or matrices in MATLAB, PyTorch also operating on tensors, which is the same thing as the matrices in MATLAB. You can start, after import PyTorch, you can start declare an empty, so-called empty tensor, which PyTorch initialize with random numbers. But don't use this as random initialization because it can contain any value, including not a number. So you might run into big problem if you use that as random initialization. So the basic syntax is like this. Torch, which is the module you're trying to use, dot. This is saying this method belongs to this specific class, empty, meaning declare an empty tensor. So this is the proper way to initialize random matrices. Of course, we can do with initialize zeros, five rows, 3 columns. This is a long type, which you guys can search after the class. It might not matter when you do the operations. But when you counter arrow saying this type and that type doesn't match, you guys can search for what does it really mean by long type, float type, CUDA float type. All of those things are pretty available online. So all of this are just very basic. We'll just run through that. Now you can declare a tensor with specific content that you're interested in. And all right. So this is the thing that will become very useful, the size. The size method of a specific tensor. The tensor, once declared, you can use size to check the dimensionality of this, just like the size in the MATLAB. All right, so this is very basic stuff. And then another thing is called view method, which you can understand it as a counterpart of MATLAB's reshape. So if you have a matrix and you want to reshape to another dimensionality with the same number of elements, you can run view, right? So if you see let me see here. Right, so if you see this size is a 4x4 matrix, but view 16 changes to a vector of 16 elements. And then view this is change, -1 means it's flexible, and 8 means I want 8 columns. So now it becomes 2 rows and 8 columns. So this is basically just a reshape. View, some of you might thinking view is a stupid name. They name it as view because you really just view the matrix in a different dimension, not really changing any contents in the matrix, which is a kind of different from MATLAB. All right. So all of those are, let me see. Okay. Okay. So I think basic idea of the tensor is there anyone have any question of this kind of basic operation? No? Okay, good. These are very basic. So all things I'm just go through and you can refer to later when you're doing your project. So second, this is probably one of the most important thing of any deep learning packages. So why a deep learning package can be so popular is because a specific type of operation that it can do is the automatic differentiation. So before the automatic differentiation is widely used, any deep learning package requires you to manually derive the gradient for the loss function and with respect to each layer. So that can be quite intensive when you're trying to do the backpropagation to update the weight of the deep learning network. Did Alish cover deep learning already?
You haven't.
No, haven't. So, any of you know more or less what the deep learning is? No? Yes? Okay. So let me just cover a little bit. So why it is an important technique. So deep learning package, deep learning, it comes from the just regular neural network, where the regular neural network is nothing but a linear combination of the inputs and passing through a nonlinear activation function. So once the nonlinear activation function is fixed, the only parameter that can change is the weight, right? The weight that you do the linear combination. So that are the parameters you want to do the optimization. So the neural network repeatedly apply this type of operation. Linear combination of the inputs, then passing through a nonlinear activation. And then the output of nonlinear activation will be yet again an input of a linear combination and then another nonlinear activation. So this is an embedded function that becomes very deep, and it becomes, people usually just call it a deep learning or deep neural net. But the problem isn't so why it wasn't quite popular before, it was, the idea is very simple, and because we don't have that amount of computation and that amount of data. Because when you consider how to estimate this function, which is defined by all of those weights, you have to optimize every weight and at each layer. The method that proposed before is called a backpropagation. So when you say backpropagation, the conceptual understanding is you have the outputs provided by your network. Now you have a ground truth output. That's the target output, which is the real output that the network is supposed to provide, or ideally it's supposed to provide. So it makes mistake. So you want to do a comparison between the predicted value and the real value. So that's the arrow. And you want to backpropagate that arrow with respect to every single weight. And then you can find out how much I should change of the weight. So that step is done by gradient descent. If any of you take the optimization method class, it's just a regular gradient-based method. It goes a little bit more complicated when you go to stochastic gradient descent, but the basic idea is the same. So if you want to calculate the gradient with respect to of the or let's say derivative of the loss function which defined how you measure the error with respect to every weight. You have to do differentiation of at every layer level. So AutoGrad, which is the automatic differentiation from the PyTorch, help you to do that, so that all the basic operation, convolution, summation, multiplication, or sine, cosine, most of the operation you can imagine, it already provides you the gradient or the derivative that is you're supposed to use. And the algorithm will take care of deriving what are the correct form of the gradient. So let's see how much I should go into this. Any question with respect to the thing I just mentioned? Right, good. So requires grad, which here, when you initialize a tensor, there is a specific flag that you can give to PyTorch saying, I want this tensor to remember all the operation that applied on this tensor. So the way that automatic differentiation works is you have variables, and each operation you do on those variables will be remembered. And there is a table. You just do a table lookup of the table. The content of the table is, for this operation, what is the derivative I supposed to use, right? Sine, cosine, or even the multiplication. So you have all those tables saved somewhere in the PyTorch, and when this specific operation is called upon this variables, those derivative, those formula will be used to calculate the gradient. So that's one is saying the tensor. You can put a flag of the tensor saying, I want PyTorch to remember what are the operation is applied on this tensor, so that when you want to calculate a gradient, it can backtrace what are the operations. And so once the required gradient is set up to be true, and you can apply whatever operation is allowed in the PyTorch, and when you want to do backpropagation, it's very simple. You just say backward, right? That specific tensor backward, and they will calculate the gradient with respect to every single layer that you specified. So this is a little bit more. These are the things I say, like a little bit more detailed and understanding that PyTorch may encourage you to understand, but I don't think that's required to use the PyTorch in your final project. So I'll skip that part. And if you're interested in the materials there, and you can just go check it out. Right? And if you have any questions, you can just send me a message through the Canvas. So now, having know what is tensor, know what is automatic differentiation, let's go very quickly through an example of classifying objects in CFAR10, right? CFAR, I guess all of you guys are already pretty familiar with the CFAR data set in the project. And here we use the Torch Vision. Torch Vision is just a package that's saved. You can call to download all those data sets. So let's do this. One thing that you might worth noting is the range of the images that you want to put in. So the nonlinear activation, whatever sigmoid, tanh, all of those has specific range. It's not from, so our regular image is from 0 to 255, but that's out of range for all of those functions. So if you use 0 to 255, meaning unprocessed raw image, and have the machine to learn that, the machine is not going to learn, because out of the range that machine can predict. So what people usually do, people usually scale it, and scaled it between, center it around 0 and scaled it between -1 and 1, or minus 0.5 and 5, depending on what you want to do. So what this transform is doing, you can write all of those by yourself, by the way, but the basic idea is to pre-process the image to make sure all the images are within the range of -1 and 1. Then what we want here, this step, is just to download the training data set of the CFAR. So let's just run this. So for the sake of presentation, I already downloaded. And just for fun, let's see. But, oh, okay, so I guess. But it still shows the image. So here is a couple of examples, 4 examples of the images in the CFAR10 data set. So let's see. And now what we can do is we can start defining the network that we want to use. So the definition of the network is showing here. We want to, these are all the operations you want to do. So those are just defining the filters. And then once filter is defined, one very important aspect of this PyTorch is you have to define the forward function. So forward function meaning, given an input, what are the operations that you want to apply on the input? So those will be remembered by the automatic differentiation algorithm. So here what it says is, for the given input of x, it will first apply convolution 1, which is this, and then next apply ReLU, rectifier linear unit, and then it will apply convolution 2, and it will reshape the tensor, and go through 2 fully connected layers. And that's after 2 fully connected layers, that is, and also the ReLU, that's the final output of the network. So, okay. All right, so what we talk about the gradient descent part. Once the network is defined, you also want to define your loss function, the way that you measure your error. So here, we're doing an object recognition problem. We're using a so-called cross-entropy loss. I think Alish will cover what it is. It's basically maximize the odds of the target class. So once this criterion is defined, so now you have the loss, you can do derivative of the loss with respect to each layer, the parameter of each layer. And once that's done by the PyTorch AutoGrad program. Once that's done, you want to modify your weight in the direction of the gradient. But how much? How much will be determined by this thing called optimizer. The optimizer will say, I start with learning rate 0.001 with momentum, and that is defining. Sometimes it also modifies the gradient direction, but most of the cases, it defines how much we want to go, how much modification we want to have on the parameters with respect to the gradient direction. So in this example, we just use the stochastic, very simple stochastic gradient descent. all of those are defined, and now it's time to train the network. So when we train a neural net, this is usually trained by mini-batch stochastic gradient descent. By mini-batch is each time you only pass through a small set of images. Let's say you have batch size of 64, you only pass through 64 images. And network will use all of those 64 images, calculate the loss, and do the backpropagation update. And that you will repeatedly do that multiple times. And this mini-batch stochastic gradient descent is with respect to, or the counterpart is so-called batch gradient descent, where you pass through all the images and then calculate the loss and do the backpropagation. And then you pass through all the images again, because one iteration is not enough to learn. You pass all the images again and do another round. Because it's very computationally intensive, it takes a lot of memory, and sometimes it even converges slower. So people develop stochastic gradient descent where the gradient direction is now a stochastic process, and each time you want to load a subset of images, which is coming from this train loader, which you guys can refer back to the train loader later. I don't think you guys need any modification on that, so I didn't really cover this. Like, you can call it batch extractor. So once the train loader takes all the images or the information of all the images, and every iteration it gets 10 images, it gets another 10 images, and which saved in this data variable. So data variable, depending on how you construct, in this example contains two parts, input and labels. So then we have all the data. Then we want to do the optimization. So first thing, start with remove or like zeroed, assign 0 to all the gradient, or all the assign 0 to all the gradient, because we want to calculate the gradient. And we don't want to, so if you don't do this, like this step is not there, the gradient will be accumulated every single step. And when you do this, or backward or step, and this, the direction that the optimizer will go is the accumulated gradient, which is not the case in this example. It might be the case for you in some future work, for example, in the recurrent neural network. So after you assign 0 to all the gradient, very simple, you define your net, you define your neural net, take the input, you get the output. So you get the output, which are the labels, or the odds of the labels. And then you compare the output labels with the ground truth label, then you will get the arrow. Get the arrow, and you do the back propagation, and then you do the descent, right? So this goes through all the training data, and it goes through all the training data twice. So here is where you can control how many iterations or how many repetitions on the entire training data you want to go through. So I guess it start training. Yeah. So when it start training, it's a good practice you plot the loss when you start training, because if the network is not functioning correctly, you might not see a decreasing of the loss, which is supposed to be the case because we're running a descent algorithm. So here you see that every 2,000 iterations or mini batches, it plots the current loss, which you can see is nicely decreasing, which indicates our network might working properly. Okay, just wait a little bit, 2 epochs. Any questions so far? No? Good.
define one network as one tensor object?
Well, one network is a sequence of operation that applied on tensors.
Oh,
Right, so those are functions. So you define network as the function of, so it has this convolution, this fully connected, that fully connected. Those are all operations. So then those operations apply on the tensor. That's your input, which is, it's not here anymore. Which is the input here. That's the tensor. Yep. So now the network is finished training. It's only 2 epoch. Don't expect too long. Then what we can do a testing, right? And then we test a test loader, which is the same thing, which is load another batch from the testing samples. And we want to see what are the prediction. So let's see. Before we see before we check the prediction, let's first visualize a couple of examples. You can see the testing example: car, sheep, plane. Those are testing sample we'll be using. And so as you may notice, here is the image, which is the images that we're plotting. And this image go right through the net which is the network that is already optimized with 2 epoch of stochastic gradient descent we just ran. So this is, you get the output here. So this might not be very meaningful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are corresponding to the logic of 10 classes, which we want to have the maximum. They want to get the maximum one. The max operation is doing here, and the output, which each of them corresponding to the likelihood of each class. So here, let's see what the network says. The network says is cat, sheep, which is 1 arrow. It's not too bad. And so this is just one example, and we want to check how is the network do, like what is the classification accuracy for each class. So by running this is basically just running through the entire testing set. So data is a minute batch from the testing set, and you just keep iterating through the mini batch loader so that all the data is iterated through. And every time you just get a bunch of images, a mini batch of images, pass through the neural net, get the output. And then you just calculate how many of them are correct. All right. So let's see how many of them are correct. So the accuracy here, which it says is 51%. The chance, which is at 10%. So for each class, now you can see for each class, we can also calculate the classification accuracy. The accuracy of dog, which sheep, is pretty good. Horse is pretty good. The cat is not so much, but they're all quite above the chance, right? So that's that are the things you might want to report if you want to do your final project and write in that into your paper. There are many other metrics you may want to use. You want to see how the one class is confused with other, which you can use the confusion matrix. So then it's basically it. And at the very end, how do you run in GPU if you have a GPU? Very simple. You just do torch. You just get the device, and for every net. By the way, by default, they're all run in GPU unless you specify saying I want it to run in CPU, right? And So which I think here. Right, so here is device is the device number for which GPU you're working with. And whenever you declare everything that you declare, tensor, neural net, operation, you can specify tensor.CUDA, and that will feed that specific tensor into the GPU. And then it's from then on, the tensor will do the operation in GPU, and you take advantages of the computational power. All right. So that's basically it. And any questions in general? Pretty confused? All right. So if you don't have any question, like I won't keep you guys. Just feel free to. Yeah, sure.